Hi, good day everyone. Thank you for attending this webinar. We will talk about what a well-trained model can do other than predicting on new observations. If you are puzzled by these questions though, think about a situation where we have a prediction model in a factory to predict yields, and it started shooting out alerts since the model has predicted something wrong, be it minor or critical. At this point, the foreman in the floor may need to take some corrective actions. For example, adjusting some controllable valve to a certain extent. So we will be asking the model or the system for corrective actions rather than predictions. And this is prescriptive analytics, if you will, instead of predictive analytics. My name is YC Lee. I'm an AI project consultant with Scientific Formosa here in Taiwan. I have been a consultant for the past 10 years. Before that, I have taught and then worked in the US first, then in Taiwan for more than 20 years. Okay. Now here's an example of petroleum bitumen production. Okay, so you can see some of these containers, condensers, or the control involves. So we do have a set of records that include some output attributes such as the yield. Okay, then we also have some controllable settings such as the steam flow rate and others. And to the right, we have some non-controllable features such as outside temperature and pressure. So the use case is to adjust some controllable valve for the best yield when actions are called for. For example, I'll try to adjust this condenser temperature by a certain degree. Okay. Now with this bitumen example in mind, we are in a better position to feel about the pain points here. First of all, the business challenges are like this is a batch production, and then there's some inconsistent degree of the input reactant, like the bitumen itself and the solvent, right? And then the yield is highly dependent on the external factors such as the temperature, pressure, and adjustment in the real time to maximize the yield and the income, including something like a natural gas steam flow or air temperature or the condenser temperature. So specifically, the pain point as this: the adjustment must be constantly made in order to get a better yield, something like that. And the adjustments are manual and reactive. And then it relies on the experience and the intuition of the workers. So onboarding of the workers may be very slow, and it's potentially error prone. And between the workers, there might be quite some variance. Okay. So now it'll be terrific if we have a dashboard as we show here. Now, first of all, these are the fixed, mostly external features here listed. And then we have some readings of the current settings, right, for those controllable parameters. And then the model, the prediction model is working, so they can predict for this current batch what is expected yields or the margin, right? So as we talk, right, and the system is smart enough, so they have some of the optimization work running behind the scene. So they will come out, say, for the current situation, the system will recommend these settings for the controllable valves. And then of course they can show you if you do as suggested and what kind of improvement we may get, the percentage of the yield lift, the increase, or the margin increase, right? And the system can definitely keep track of this this trend for the difference between the original setting or the recommended setting, and then some of the margin changes. Okay, so this kind of dashboard would be very useful in an automatic kind of product. Let me first provide some background information for the whole set of tutorials here. And today the tutorial is number 6, right? Basically, we prepared this set of tutorial from different data prep perspectives, and we accompany them with an end-to-end scenario to illustrate the corresponding techniques to realize some of the concepts involved. Now you may ask why? What is the motivation and objectives, right? RapidMiner is powerful and easy to use. But we still see many customers of ours that struggle to become better at RapidMiner. And one of the key reasons, as we came to realize, is that the creativity and instincts is somehow limited when the users are presented with the problem for machine learning, right? Oftentimes, we do not know what attributes we can and should have in order to formulate the problems. By problem formulation in this context, we mean that there should be a clear statement for the problem that includes what attributes should have and should be ready before the model training, right? Therefore, in order to leverage RapidMiner, and our objective here are to highlight those concepts and techniques that are surrounding all this data sets transformation. Such knowledge will come in handy when we are presented with high-level and mostly vague business problems. It helps us to come up with different alternatives for the problem formulation and also the format of data sets that we should try to come up with for the model training. So here we will talk about this tutorial, right? But anyway, there are prerequisites for these tutorials, right? And RapidMiner is so powerful that includes more than 1,000 operators. We don't really have to learn all the operators before we can master this platform. So just make sure that whenever we are learning the operator, and we try to make sure we understand all the parameters, and we also try to dig out the tutorials from the help section to show some demo to ourselves, right? So the number of operators that we have been exposed to can be still a very limited number, but we will get to be comfortable with the platform first. So if following these circles, you do know that there is something you should do, like monitoring the performance, the resource usage, or have the log session for debugging purpose, etc. Now with this kind of knowledge or the level of confidence, then we go to take the tutorial, and that will be very useful. Okay. Now back to the focus of today's tutorial. It is all originated from the notion of model interpretability, if you have heard about that, right? And the founder of RapidMiner, Dr. Ingo Maswa, that he had a talk maybe 2 years ago, and that he highlights the notion that many people view most of the model as black boxes. It is not clear how they create their predictions. So he urged everyone by saying, try to explain your model and then earn the trust from the others. Is that important? Yes, it is very important, because no matter how good you are as a data scientist, the purpose of your effort is actually to come up with a good model and convince the domain experts or the operational folks to accept your model and to trust the model. Okay, so the motivation here is that why so many machine learning models never put into production, right? The designer may not understand the specific behavior of his model during individual predictions. So even though the overall performance of his model looks good, the designer may fail to convince himself, let alone winning the trust from the team. And RapidMiner actually first featured these things like interpretation, simulation, and optimization function in its auto model. Right? They will use some of the confidence distributions for classification models or prediction distribution for regression models. And then they will allow the users to clearly see the contribution from various feature value pairs. Now, the local importance values, where do they come from? They are derived from the correlation of neighboring predictions. This is not a generic whole data set type of property. It's just a neighboring predictions, right? So to explain the individual predictions, simulate local inference of the feature value, and furthermore to support feature value optimization. Okay. Now the objective of this tutorial that is to cover the key concepts and demonstrate, as that's what is always the most important things for us to go through in the tutorial. So we will show some real classification and regression examples in areas of manufacturing, tuning, and long application. And we will show it not only the manual mode in the auto model, but also the automatic mode in the studio. Maybe that's our RapidMiner just did not have enough chance to expose this particular feature, the explain, simulate, optimize, to the users, or the user just jump to conclusion too fast without making sure they understand all the concepts are involved. But the most important thing is here is that we have trained the model. We are just trying to use this trained model to simulate some particular set of attribute values, right? And all we will try to use this model to optimize for some parameter values subject to some unchangeable features, right? This is fairly clear, but you can see from the community some people would have misunderstanding like this. Say, I trained a model which is relatively good, okay, but the user did not have the notion of this is actually after training type of things. So he simulated that, and the confidence level at a particular set of attribute value actually dropped down to 55. So the user is confused, say why a good model would turn out with such a low confidence. Then he further pushed down the optimized parameters, and when it's optimized, the particular set will reach the fairly high confidence level, and this time the user is even more confused, and he's saying, well, maybe after optimization the system already improved my model and give me a model of 90% confidence level. This is not the case, right? The system simply gives you a set of parameter values that will reach the highest confidence level. Okay. Interesting, there's more misunderstanding, right? This is probably from an instructor at the school, and he said that he likes the auto model, which is very useful, but it's manual. If the model gets complicated, the interpretability gets messy too. And he has found something like Lime. It's just a toolbox. Actually, Lime, you can read this paper out from 2016, right? It's fairly clear. At the same time, about the same year, there are actually other type of approaches that you can always read it if you have time and are interested. And the basic idea is that, for example, you have the case here, two features, and look at that in the center of that heavy red cross. And if you move that cross a little bit to the right, immediately it'll change the classification results. But if you move to the top, to the left, to down, probably classification will not be changed too much. So this local behavior by the algorithm will be calculated, if you will, or depending on just the neighboring points. So here, for example, these points overlap with the green triangles. 8 of them will be the one, exactly the one used to calculate the local dependency. Now, of course, the algorithm will have some of the smart mechanism to decide what are considered as the neighboring points. And when you try to do further things like later to simulate or to optimize, definitely some of these smarts will be used in those algorithms as well. Now, it's just interesting to see what is the response in the community from the RapidMiners folks. And some of them say, local interpretation is a link, the Lime algorithm. And somebody also say Lime is actually part of the operator box. But I think this last one, if I remember correctly, is from Dr. Ingo Mauswald himself. He said that the operator explain predictions is creating those local explanations in a non-manual way as well. And it is an improved version of the Lime, which is in general faster and can also handle all data and the prediction types. This improved algorithm is also what we used in the background of the model simulator. Okay, I would argue it's also in the background of the optimization function. Okay, so just to clear a little bit, okay, we talk about optimization so often, so much in the machine learning, right? Typically, we talk about optimization model performance. That is before a model is built. We optimize the selection of features. We optimize the parameter of the models for the algorithm. We optimize the hyperparameters for the configuration of the model architectures, right? But here we are talking about the optimization test after a model has been built, been trained, I mean. So for regression models, we optimize the selection of feature values toward the highest or the lowest prediction value or toward specific value, right? Either way. And then, but for the classification models, we are optimizing the selection of feature values to achieve the highest or lowest confidence value or reach a specific confidence value. So this should be clear. So our mindset now should move from predictive to prescriptive. And RapidMiner did have a webinar that is virtual optimizer about 2 years ago. The speaker is from Europe, relatively young man, but is very smart. Now, his 2 main points are that with machine learning, one can surface insights via interactive dashboard for making decisions quickly and easily. I think he actually meant this dashboard is automatic, but it changes whenever this external situation changes, right? And the second point of his is that process optimization through the lens of RapidMiner's virtual optimizer. This is a real-time prescriptive dashboard that lets workers understand the current state of the operation, experiment with potential changes, and then implement the best solution. Okay. Now look back this bitumen example, right? For example, we would like to optimize the yield, and the current situation is highlighted by this circle is the current outside temperature, and outside pressure is like this. So we would like the system to optimize the value for these 3 controllable valves, and hopefully they can come out with some parameter settings we can adjust to, and in order to optimize. So the outline of this tutorial is as follows, right? We do know this is all centered around the notion of model predictability. So first of all, let's make sure that we understand some of the basic concepts. And be careful about this weight we usually talk about. A generic weight, or the model-specific weight, or the feature importance, right? And because using that, we not only do the model interpreting, but we also do the simulation and optimization. Now, for this particular functionality altogether, we're doing two modes. One is in auto model, another one is in studio. On the auto model, it is mainly this interactive process where we follow all these guidelines in the auto model, and we can check all the weight along the time. And so you will see clearly the model specific weight, and then with a highlights of the feature importance of each prediction. And there we can do the simulation and doing the optimization, again following the instruction on the tool, right? Now, however, if we want to put this into operation, meaning like what we show in this dashboard, we would like to have a RapidMiner process that running on the server and automatically. So we need to come up with this typical regular RapidMiner process where we use operators to automatically do this optimization to generate the recommendation. And now we will show some different operators. They are become available at a different time. So we shall tell you how to use them, and you can play with them for your own purposes, right? So the repository we have prepared for our hands-on workshop is like this. And now we will just, like what we said earlier, we do proper data preps, and then we will run into two different cases. One is for the bitumen case, and the other one is for loan application. So it happened that the bitumen case is a regression optimization, right? And then for the loan case is a classification. So we will see some basic difference there. And along the way, we will introduce the operators that are the key here. Okay, first of all is that on the auto model, what we can see. This is a review if you already play with this in the auto model. So now let's first talk about how to play with these features, the interpret, simulate, and optimize in the auto model, right? We can take that data that is already pre-processed and ready for the auto model. And once we run it, and you pay particular attention to the left part, in each model, they have their specific things for us to look at or to play with. For example, you look at a simulator, and inside there is also optimization for you to play with. Now, it's important to see that under deep learning, we have the weights. This is the model specific weight. Okay, they kind of collect all the local dependency and summarize them to make a model specific weight. Now it's different from the weight down there under the general category, right? Those weights are what we are familiar with. So we usually take the data set and run correlation and come up with a generic weight for the features. So we run those three algorithms, and we come up with the performance metrics for this case is a regression, right? And here you see this root mean square, the absolute error, the relative error. And the numbers, you probably can tell that deep learning is better one. So if graphically you look at the curve, I think you will choose this deep learning as well. Okay. But this is nice to show the model's performance. But if we look at the weights here, right, as we mentioned that this is a global weight. We take the whole data set and run some correlation, and we take the the correlation of the dependency of yield on other attributes, and we come out with a weight by correlation as shown here. But if you go to individual model after training, you can see that this model specific weights are quite different. They look similar, but still some variation between all these three algorithms. So you would ask, right, how RapidMiner come up with those model specific weights? Okay, here for all these algorithms, we can see that actually you can see from the auto model, for example, for GRM model here, and they show 4 records, and the color shaded for this parameters. That's all. The color is to say how important the particular feature value is to the prediction, the contribution of it, or in the positive way or in the negative way, right? So you can see that for the green is to support the prediction. The more the feature value, the higher the prediction would be. So it's kind of weight on the current parameter value, right? The darker one will actually gets heavier weight. And on the other hand, that contradicting factor is shown in red. And the more the feature value, the lower the prediction value will be, right? Now, how exactly they color them? So, you know the answer now, right? They use the Lime algorithm to calculate the local importance for each attribute here. For example, the preheated temperature or steam flow rate and the condenser's temp, I think. All right, so when they calculate all this for all the record participating in the validation phase or the testing phase, that's when they have the prediction, right? So they come up with all this local importance, and you can see that the distribution, okay, is like this. And on the top is that preheated air temperatures distribution is very much like that. And these are all the testing records they have run. And so they come up with this distribution, and definitely they can just summarize them to become this model specific weight for deep learning, okay? So here we comes into this simulator. Once we click that, you will see immediately they have in the center that is a deep learning. And all these scale, these rulers also always pointed at the center point here. The center point is actually the median of that particular feature in this data set. So 71.719 is the average condenser temperature. So by default, they start the simulator page with all these median values. So if you say move at this particular feature that is preheated air temperature, they will show the histogram of preheated air temperature, and the average value is here, right? So this is, first of all, it is where how the interpreter is set at to explain the models. So when the parameter value is like this, they will tell you this, the prediction, the yield is 4,000 something. And then remember, this is green color, meaning this particular feature is a supporting feature. And this red one here is to say steam flow is actually contradicting. It's the negative impact on the final value here. So if we look at this and we try to say, well, and we just talked about a regression case where the result is easy, that is just to predict a regression value, right? It's a value we try to optimize with. But would digress here a little bit just to talk about the case for classification problems. For classification problem, for example, this binary classification, we will show as a result is just 2 confidence levels here, and the winner is the worthy one, right? It's at 85% confidence, and so the prediction result would be this one. So again, this left panel, their attribute will sit at their median value to start with, and to the right we have two bar here to show the confidence level, and down there please note that all this supporting in green or contradicting in red, they're corresponding to the winner here, meaning the green one the higher will increase its confidence level, and here the red one, more of this value, they will decrease this value. So if you want to adjust the savings, you should do the other way around. You reduce it and the confidence level will be higher. Okay, now we'll get back to this loan application later. So now back to this bitumen regression case, right? So we can see that once we open it up, this interpret mode, and we see that all the average value will contribute to the yield 4,160 something. Now we look at the first attribute, which is the preheated air temperature, and that is supporting feature. So the more value we give to it, we should be able to increase the yield. So what we do is now move this a little bit to the left, and as a result we should see a higher yield, right? That is doing what we are expecting that to do. Now let's look at the second feature, that is a steam flow. It's red, so it's act in a contradictive way, right? So the more, if we increase that, they will lower down. So instead, we are going to lower down the value of this steam flow, and reversely, we should see the increase, right? So that very much explains that how the supporting features with their weight or the contradicting features with their weight will affect the final result. Okay, of course, once they reach to this stage, the weight changes. We can see steam flow is still a negative, contradicting feature here. Now, when you try to prescribe, that's another story, right? We just talk about some simulation. We can see what's something good. If you're happy, you can stop at where you see a higher value. But if you want the system to optimize, this actually down this value selection panel down there, there's a optimize button, and once you hit it, that will do the job. But here, let's do a quick summary. Okay, for this simulate feature, when we come in here there are actually three goals. First is to interpret the model, right? We can see what attributes are contradicting, what attributes are supporting. Then later we move around the attribute values, then we will see how the result will change. But the third part is what we call the optimize. We can use this built-in optimization method and to set the constraints, and then as a system to reach the optimized parameter value. So this actually turns the predictive model into a prescriptive model, and that's what we are going for at this point. So once you hit the button, we'll be guided into some steps. So for example, for this optimize things, we want to maximize the yield. That's the regression value we try to predict, right? And then we have to say some general constraints, right? For example, we like to stay within 2 standard deviations of each attribute value, and we should not go beyond the existing maximum for some higher value we have never seen. And same thing for the minimum, we should never go below, right? Oh, this is, you can of course choose not to click that, but anyway, down there you have some constant attributes. For example, we need to add this outside pressure. So we can use that plus sign to add this outside pressure. And of course here, for illustration purpose, I already enter outside temperature at 19.297. So we are given all this constraint, the general constraint or specific constraint, the constant constraint for the non-controllable attributes, right? So now if we can wait, no time limit, no generalization limit or whatever, so we just choose no limit and then let it run, right? Now this is the final result. We can see that they have reached the saturation point, and that finished this. So quickly here is that we have earlier two simulate steps. First is to adjust preheated air temperature, and then second we do lower down the steam flow, and we can see that yields actually changed, actually got increased. Now with the optimization, the screen will show us the new yields, right? And then we at that point what kind of weight they have. But basically you can look at this value panel here and look at those three controllable variable, and you should be able to see the value has been changed, and as we highlight here, and so is the final yield, and that has increased to more than 4,800. Okay, that very much explained to us what this optimization can do, right? Now let's try not to ask this particular feature to too strict sense. By that I'm saying here we don't have a mathematical model to fully describe the system behavior. Instead we use a prediction model to mimic the behavior of the model, right? And we run different process with some randomness selection of the testing feature or training steps. So there will be a lot of randomness there, but just look at the result here. It actually suggests us some corrective actions, and indeed they will increase the objective, that is yield in this case, right? It's not to attack anyone else, but so many people have been talking about the power of machine learning and telling that the machine learning can learn everything about the system and tell us exactly what to do. But when people say so, hardly that many people have really run the prescriptive cases, right? We just kind of through our imagination thinking the system should be able to do that. Now here is a case for you to think about it, right? And this is a case where we really run, even though it is simple, you can see that how the corrective actions can be generated and can guide the operational people to set the parameters. So that's what we call parameter tuning, right? So up to this point, things look good, and we can do on the auto model interactively, meaning we can simulate it by hand, we can optimize by pushing a button, right? But in the real case, when things are operationalized, what we usually like to see is we have a RapidMiner process designed and tuned on the studio, and we let it run on the RapidMiner server, that's an AI hub, and through the API they will talk to the application in the manufacturing floor, and that will be automatic, meaning whatever external features will be sent into this process, and the process along the way optimize for the desirable corrective actions and then send back to the application. That is where we need start thinking about RapidMiner process, so that we can do automatically instead of manually in the auto model. right? So you see here we just try to introduce what they can do. This is not 100% automatic yet. We will just gradually showing some of the operator. Okay, so you can see that we take the data and we can send into two particular operators. One is explain predictions, and the other one is the model simulator. And let's talk about them separate. First, this explain, right? And they have 4 output. And the first one is for what we have seen in auto model, and it's colored confidence levels, right? Or we call the local importance, right? This is for us to look at. But for processing things, we probably should have some data that is ready to send in to the subsequent operation of the code. So you will see this is the same thing, but it's in different format where you have key attribute pairs. For example, look at this preheated air temperature at 104 and with a local importance 0.841. The same thing for other predictions, right? So the third output actually just try to do one more level of processing to extract out things from that second output. So you can see here they put nicely in the different rows, right? So for preheated at air temperature, the value is that, the importance is that. So with this table, definitely they can quickly sum it up and to have the model specific weight as we talked about earlier. The second operator, simulate and optimize, is actually something we will do also interactively. By that I mean we have the previous flow run up to this point, and then when we click the simulator, right, we will see something similar to the auto model. But knowing this, the previous process may not be the process that auto model has been doing for the model training or something. So the way they pick up the data or the way they split it, whatever, they can be different, and the algorithm can be different. So the result here we are going to see for simulation optimize will be different also. But hopefully this is following the right direction we are expecting, right? So the same thing for the input. We can do some simulation play around here, and then also we can see the optimize. We click on it again, we come into this and then click optimize. So we will follow along the same step of optimization, and we should be able to come out with the optimized result, right, with the adjusted value. So that's the recommendation we're looking for. But anyway, this is all nice. And as a summary, we can see that earlier in the auto model, we optimize for the attribute value, and we can see the yield expected is like that. And now we do on the studio, we run it through our process, but at the end we look at the simulator operator. We do very much the same thing, but the value are slightly different. So as I explained, right, the general direction is the same, but the specific value may not be the same because the leading process before the simulation operation is different. The randomness and some of the parameter setting is different. Okay, but that doesn't affect too much of this general. Now, if we recall this particular dashboard, this is exactly when we have to have the process running on the AI hub, on the server, and through the API talking to the application, so that we can read in external parameters and do the optimization and send back to them the recommended readings, right? Here we definitely need to have another operator. But let me just caution everyone a little bit here. Okay, this prescriptive optimization operator is a little bit old. Well, 2 years old. When this particular workshop by webinar and was given in 2 years ago, that time they only have this operator. This operator is also in the form of the extension. There you can pull out this operation and follow along to do the optimization. But since then, and during the past 2 years, I don't know exactly when, the RapidMiner come out with a different operator inside its main system, right? The operator has, as far as I am concerned, easier and a cleaner interface, the parameter specification to use. But this depends on people. Some people may prefer this old one, and some people may prefer the newer one. I will just introduce them both here, right? And so for this prescriptive optimization, there's some parameters you have to set. Again, it is basically to say what are adjustable, what are not, and you can read it. And then something here, as I mentioned earlier, we have to first, just for illustration purpose, we create this example set so we can run the optimization, okay? But in reality, remember, this process is to take as an input from the external web application the fixed environment features like a temperature or pressure. And then once they get it and do some optimization, they will generate the values for those controllable parameters and send out these parameters out back to the web application as the corrective actions. So here you can see that I'm putting those 3 variables as a macro, those controllable ones, right? And then for illustration purpose, I take these outside things as a constant, but in real time they will be read it in from externally. But anyway, with this, we can go all the way into this prescription optimization. In there, we then put it in the model, and we will generate attributes and the performance. And what exactly they are doing then is the general attributes is, again, for RapidMiner, they are strict on the attribute types. So what we are playing around is this prediction yield, right? So that is a special value. So we just try to rename them here as a residual and make it a regular attributes. And then we'll go through the performance to extract this performance values out. But anyway, you can play, and that you should be able to come up with, and then with proper renaming, okay, because some of the name are system generated and not readable, and the residual, nobody knows what is a residual when we introduce them as just a temporary name. So at the end, you can see that the output will be some of the readings, and some of them are what we are looking for. These are the controllable parameter values, but others are the like outside temperatures or the outside pressure, right? And then at the end, of course, is the optimized yield. And just a quick summary here is that we actually run 3 different methods. The first one in the auto model. Second one is similar. We run on the studio process. And the last one is we use the operator to automatically perform this optimization method, right? Again, the yield they generate is slightly different, and then the adjusted parameters are also not exactly the same, but they are following the general directions. That is good. Okay. We talked about regressions. Now let's move to classification. Here I will talk a different use case, right? Because earlier bitumen is a regression things. So the data set we are using is actually available in the tutorial of the prescriptive optimization operator. So you should be able to find it out, locate this operator, and check its help section, right? So here the problem is a classification problem, and we try to predict the credit worthiness, meaning to accept or to reject a particular application. Now, we would like to also calculate most attractive combination of credit amount and duration for specific customers. That is interesting, but we'll see soon, okay? So here is a case like we have all these loan application cases for us to train about. And the attributes include like the purpose of the loan, the saving they have, and what kind of employment history, and the housing, a job, or duration, and credit amount. Okay, but there's two important parameters, right? One is the duration, one is a credit amount. You do know the different combination will involve different kind of risk, right? But the bank does not want to reject whatever they don't feel comfortable with, right? Sometimes there's a negotiation process. They would like to see maybe I cut short of the duration or lower down the credit amount, then the particular loan will get a higher confidence. And that will be good. Both sides will be happy. People get a loan with a little bit lower than what they expect, but still get the loan, and then the bank has a business. But anyway, this is an optimization problem we can play with. So move on to this auto model. Just let's go very quickly. Okay, I take the data and run this. And then in there, I would like to do optimized for highest worthiness confidence, right? So be careful about this, the step that I put in the left, so that we can go very clearly exactly what we are doing. First, we will try to predict or simulate the worthiness of the application. This application is like that, asking for 15,000 and for the duration of 24, right? So we try to run the prediction, and turns out that we should reject this. So that's definitely turn away the customers, right? So we will try to optimize. The second step is to optimize the highest credit amount and duration that the bank can accept, right? So a lot of attributes that should be fixed. So as we point out here, cross meaning those are the constant we should send in, and the only controllable things will be the credit amount and the duration, right? So the result come out saying that, well, you cut down the 15,000 down to 2,400, and the duration cut down to 4 months. Then that is when we can get good confidence to grant the loan. But this is not practical, right? And people may just walk away saying, well, I can just go do some short work and I'll get this money. So we try to optimize again. But at this point, our optimization is some kind of conditional optimization. Look at this is that we would like to optimize again, but we will lower the expected worthiness confidence. Just say the bank saying, as long as you can reach the confidence level at 75%, the loan is okay, meaning we can grant the loan, right? So when we run this set to the 75%, that's exactly how we set it, that we'll talk about later. And then you can see that, well, the money is still not much, right? 3,000 or so. But the duration can be extended to 44 months. That is probably not the customer would like, but we will see some leeway here. So at the end, we probably like to just simulate it a little bit. Remember that here is that people sitting in front of you is asking for a loan, and we can play with the system just to predict what kind of combination. So I actually do some simulation. Maybe the guy is lucky or you're lucky. You find out that if we set the amount at 10,000 and reduce actually increase duration, right? Or in some ways reduce from 44 down to 30, and we can barely reach the 76. of the confidence level. That should make everyone happy. Now, if you are happy with the previous scenario between the bank and the customers, right? And you would ask, how would that exactly use RapidMiner to do such a things, right? And the bank, the agent will probably have to click this button and to see what the system can come up with, and then later he can do some simulation to get the final things a better, more acceptable value. But anyway, here is a flow. We have to train the prediction model first. This is a classification problem for loan approval, right? So, and now we focus on this particular application that we shown earlier. So at the end, we will have to use this similar operator prescriptive optimization tool, right? So the validation, very much what you have seen. And then for this optimization operator, we run very much similar to previous case, but here is getting a bit tricky, right? Because we are not shooting for the maximum or the minimum. Instead, we just try to shoot for some acceptable threshold. So here, 75% is set as the threshold of confidence. Now, if we stay above it, that would be good. And we know the fact that if we can drive the system down to close to slightly above 75%, typically the application amount will be higher, and then the duration will be longer, right? But once the confidence level is below 75, it is totally unacceptable by the bank, so we cannot go that. So this the logic we have in this general attribute will be a little bit tricky, but you can understand that. So we just set it as something like once we are still floating above this 0.75, it's perfect. But it's below 75, we will incur a lot of penalty so we will not go down there, right? So the performance is similar to the previous case. But at the last, we have a sub-process. Here, I'm just logging. I will use some operations to log the intermediate result so as to show what the system is doing during this optimization, okay? So slide, right? See, for example, we go through this particular expression to penalize any combination that will result in the confidence level below 75%, right? So as a result, we have a fitness, that is the final goal we try to achieve, right? So it's the duration and the credit amount actually is what we really look for. The normal name is 4 months and 5,700, which is in our third step. It is a little bit too stringent, so we are doing the simulation. But anyway, before that, let's see how the system has reached that value. Again, I'm using the sub-process. At the end, we log properly and use some macro value to keep track of them. Okay, now if you're interested, you can take a more careful look into these operations that sometimes used for, so that you can follow the logic used inside the RapidMiner. So the log is like this. They just floating around these confidence levels and try to drive for the best. Okay. Now, the very last operator we try to induce, as I mentioned earlier, is the newer operator that during the last 2 years, RapidMiner has created its own operator for optimization instead of the one borrowed from the extension, right? So this is called a prescriptive analytics. And this operator does catch all the actions we have demonstrated earlier, but instead they will put in the parameter to specify all this behavior, and this become more clear. Okay, so for example, we would like to set the value to reach is 75. This is the tricky one, right? We want to set the value at 75%. And what's the value? We are talking about the worthiness, right? The confidence level for worthiness. So around the average, we just allow about 2 standard deviations for us to move around to search for the optimized value. And then we also put more constraint like the stay above or stay below. Remember earlier, we all have to follow these individual steps and manually to set it up in auto model or whatever. But here they just put in a nice parameter list for you to specify this operator with, right? And then for the constant attributes, that's where you try to enter all the existing, right? All the existing parameters that you are not going to change. Now, again, if you were doing this all automatic, then these values should be sent in through API from the web application and send in the process through macros, right? But anyway, here, just for illustration purpose, we set it a constant here. So we run it, and this operator is actually much faster than the previous operator from the extension. Okay. Quickly. Now let's take a quick revisit to Ingo's original recommendation in that seminar, and referring to all these black boxes as being unable to explain the models. And Dr. Miles Watt tried to urge people to reduce a little bit of the focus on the errors. And so the spare time or spare effort can be spent on more of this understandability or the robustness concern. And then also can allow you to be more creative to look at the models, right? And in particular, is the good approach is try to explain the model, of course, with the assistance of the tool, right? There's an algorithm running behind to show you what are the supporting factors in what kind of weight, and on the contrary, those contradicting factors with a negative weighted value, right? So the clear thing is that if the model is not put into the production, then it's totally useless as far as the business objective is concerned, right? Along the way, of course, Wally is trying to explain them, and you will probably see something unusual or totally against what the domain experts said, or your understanding of the problem. So we can try to go after specific problem and to see if I actually happen to have some kind of information leak or whatever, right? So come in here and let's summarize what we are trying to bring out here, right? And usually we talk so much about the optimization throughout this course of the machine learning. And when we train the model, we not only try to optimize the selection of the features, we also optimize the parameters of the models for the learning algorithm, right? We also optimize the hyperparameters, sometimes refer to them as a configuration of this model architecture. And instead of that, in this tutorial actually talks about the tasks after the model has been built, has been trained. So the model needs some justifications before going to the production. So even though it is built with good performance, we need to examine this behavior, particular local predictions or whatever. And hopefully that is in line with the underlying business logic, right? So we are interested in this local prediction behavior, and we examine the supporting and the contradicting features, right? And then those values can be clearly seen through the use of RapidMiner to see how these local changes will change either the prediction on the values or the confidence level on the classification case, right? And so at the end, we can do parameter tuning that is very important in the business, right? We want to optimize the selection of feature values so that we can achieve the highest or lowest prediction value or the confidence level. And we even get to more practical that instead of that, can we optimize to reach a specific value? The 75% confidence level in that loan application is what we try. Right. So the takeaway here is that we have things in two modes, right? And you are more familiar with this auto model mode. That is an interactive mode where we can automatically build a model. And by no means the process behind that is trivial. Over the years, that process behind it is getting more and more robust. And if you're interested, you should look into the exact process they have generated under the auto model feature, right? And then on the auto model, we can explain and then simulate the model and then run some optimization, right? Or reach some specific target. And on the other hand, when we want to have our model put into operation, then we need to have a RapidMiner process running on the AI hub or the server. And through the API, it will talk to the application on the field or in the factory, right? So in this case, we need some of these critical operators. And we have shown here, demonstrated 4 operators. The first 2 are for you to follow in the process, and at the end, you can explain or do the simulate or optimize like in the interactive mode in the auto model. But the very last step, if we want to automate all these optimization steps, then we need to use the remaining 2 operators. The first one is a bit older, and that is from the extension available in the marketplace, right? And then we then introduce a newer and improved operator that is part of RapidMiner itself. And through these 2 operators, we can really automate the whole process and to support operational use. Good. I think we can end here. And thank you very much for attending today's tutorial. And by the way, Scientific Formosa is a company that represents RapidMiner in Taiwan since year 2017. And it provides a technical support and professional services for RapidMiner. Actually, it has represented many popular and powerful software tools more than 30 years now. And it has helped many customers in many digital transformation initiatives. Again, thank you very much for attending today's event. Bye-bye.